In experiment 7, we're going to be working on part 2, the isolation of GOT from pig heart. In this session, we're going to be using column chromatography to fractionate GOT from other proteins, and then we're going to analyze the fractions by SDS page, and also we're going to determine the protein concentration. In part 2, the goals really of this one are to demonstrate the use of dialysis. We started that last time. We're going to see what that looks like this time, and then also particularly we're going to look at chromatography, and we're going to use electrophoresis again. This is our acrylamide electrophoresis SDS page. We're going to develop a purification table. We'll fill that in at the end, and then we're going to really overall think about analyzing multi-fractionational process. All right, so again, why do we need to do this whole two-part experiment? Well, number one, there's a need to study proteins. All right, so proteins do a lot of work in the cell. We talked about what those are before, everything from helping with disease or helping to digest foods, many other types of things, and that's important. We often need to look for protein mechanisms. We need homogeneous proteins. Again, this means proteins by themselves. And then we often isolate proteins from tissues or bacteria or some other natural source where there's lots of other things that we might consider contaminants, and we want that one thing. So that's really our need for protein isolation. We're going to get our GOT from pig heart. However, the image that is best available for GOT is from bovine, very similar protein. We think folds in the same way. But again, it's a 90 kilodalton homodimeric protein. So that means each dimer is 45 kilodaltons. They're identical. And so ultimately, we're going to be looking in the end for SDS page. Do we see this 45 kilodalton protein? All right, so again, this is the overall fold of it, and you can see some of the alpha helices, you can see some turns and some beta sheets that we talked about in the course previously. So again, we're going to look to fractionate GOT from other things, and we're going to analyze for it. Again, there's a protein assay, a general one, that we're going to do today. You see the result of that, and that's a folded assay, and that just really detects any type of protein. Even though it's generic, it actually can be quite powerful because it's so non-specific. And also with the GOT assay, we're going to test more of a specific one. We can do that one. We've seen column chromatography before. This is CM gel chromatography. We're going to look at that. And then finally, we've also seen SDS page previously, and we're going to use that for our final analysis. Again, these protein assays just remind us of, again, a general assay, like we're going to have for Folin. We often calibrate this by a standard curve, so we get a series of proteins concentrations, and then we look at some absorbance value. In this case, it'll be for the Folin at about 500 nanometers for the absorbance of a dye, sort of a bluish dye, and that's a good general assay. That'll help us. Also, the specific assay, we've done this one before, is our GOT assay, where GOT is our enzyme catalyzing some substrate into a product. Here we just list A to B. And again, because this is an easy to observe for GOT, we couple this to a second reaction with malic dehydrogenase, where we can observe the degradation of NADH. Again, this Folin assay is a general protein assay. A dye binds to proteins, it binds to any protein, it's a non-specific one, and turns the color blue, and so we're able to observe protein concentrations by looking at standards. That is, standards are solutions of known concentration, which we intentionally develop, so we can compare absorbance value to some unknown concentration of protein. And then, again, the fractionation steps can be tested. What we mean is that each step, fraction 1, fraction 2, the AS2D, column chromatography, those can all be tested for the amount of protein that is present. We saw previously column chromatography, and we talked about DE, AE, and CM. Again, just to remind us that today we're going to use a CM column, and this one's ultimately going to be cation exchange. Here we see that we actually have a positive charge, and it's actually binding. Here, it should be, in this case, it should be binding to a negative. So here. But ultimately, if we had a cation exchange, and we would actually have a B that had some negative charges on there, and then we would actually have a positive charge protein, which is what happens in CM. All right, so this is a general scheme for our DEA, but we can apply it directly to CM. All right, so overall, some of our procedure for experiment 6 and 7. All right, and so this is really part 2 of that, experiment 6. We're going to test for protein concentration. We're going to separate the fractions using cation exchange chromatography, and we're going to analyze the solutions by SDS page. All right, so for our Folin assay, we did do this, and we're going to give you the results in our final table, the concentrations of the key aspects of this. Again, we know our steps for chromatography. Just remember, we pour the column, we pour some CM gel in there, and then we collect the fractions, and we're going to test for the presence of GOT in those fractions by a quick GOT assay. Sometimes we can use a general protein assay or some other way to measure this, but for GOT, it just makes sense to use our established assay to get that. All right, so in the procedure for experiment 7, we're going to pick up where we left off in step 6, and that was with our dialysis. All right, so we've let this dialyze overnight, and again, oftentimes you can change this pretty low volume if we have a really big low volume of protein, really large volume of buffer, and so 1 day is good enough based on our history. And so what we need to do now is get our protein solution from here and get it into this beaker. Right? And so easy way to do this, of course, is just to cut the dialysis tubing. First, you want to make sure that you keep it in the beaker. So always have a little tray, a little backup container in case something spills. All right, so this is the solution. This is what we're going to refer to as our AS2D, so ammonium sulfate 2 dialysis. When we put it in there, we call that AS2. That was ammonium sulfate fraction 2. That was sort of what we went with. And so now it's been dialyzed. We've gotten rid of the salts. In the next step, we're going to leave this step, which is really the dialysis of cleaning up from ammonium sulfate fractionation. And now that we have it free of salts and lots of other things, we can now add it to our CM column. All right, so we've seen the CM column before, cation exchange, but we're hopefully going to track the GOT, attach it to the CM column, and then we'll be able to equilibrate it off and to be able to isolate the GOT more clean and more pure than we otherwise would. All right, so we're going to head to the CM column next. Okay, so we got our dialysis result, AS2D we're calling it, and we're going to load it onto a CM column. Same CM column that we saw previously in the semester, so it's cation exchange, so we're going to load our sample right here on top. So you can tell the difference in color. So a little bit of probably some ammonium sulfate that hasn't fully left, and also the color of the protein. And so it's going to start to dilute, see a little bit of dripping. So what we're going to do is we're going to allow the GOT to get into the column. I'm going to put that in. Once it gets into the column, then we have 20 milliliters of a 0.03 molar sodium acetate. This was the same buffer we used in the dialysis tubing, for the bulk buffer. And that's going to allow 20 milliliters to run through, and it's going to push out additional proteins. And we're going to collect fractions. Right now, let's start. We should just go ahead. This first couple weren't part of it, so we'll start collecting fractions, and we're going to collect 30 total test tubes. We're going to use 20 milliliters of this on top. And then once that 20 milliliters works its way through, it'll pull out other proteins that may be negatively charged. It won't be attracted to the column that much. And then we're going to move on and get 40 milliliters of a higher concentration, 0.08 molar sodium acetate. And this will be enough concentration difference that will allow the GOT to then be eluted, or that is kicked off the column. All right? right? And so we're going to basically collect 2 milliliter fractions, and so that'll be a total of 30 tubes because we have 20 milliliters of this, 40 of this, so we have 30 tubes. And as we do that, one of the things we're going to do is we're going to test for for GOT activity. We're going to do what we call quick GOT activity on every other tube. A quick GOT activity is just taking undiluted CM fraction. We're going to put it on in our cuvette and let it go for 2 minutes. That's a quick one, sort of a quick and dirty method. Say, is GOT present? And we're going to find those results. And then once we find where there's likely the highest concentration of GOT, we'll pull those test tubes and we'll concentrate them and run them on an SDS page gel. All right, so we're going to let this run. And it's going to take a little while. You can see the dripping's pretty slow at this stage, but it looks like the sample's just about all into, just a little bit more to go all into the gel. Then we'll proceed with 20 milliliters of this 0.03 buffer and then 40 milliliters of the 0.08. We tested the activity in every other tube, starting with 1, right? And we got 29. We did finish up with 30. We had, again, 29 and 30 just to make sure. But it really appears as if, this is probably our high point. So we ended up taking 26 and 27. 25 was pretty good, but we thought 26 and 27 would be our 2 fractions that had the highest concentration of GOT to isolate. And again, if you're doing this perhaps in the real world, you want all the GOT. You might take all of the fractions, say from 17 all the way up to 30 and maybe beyond, to isolate all the GOT. Our goal was just to show and prove that we actually isolated GOT. So we're going to take 26 and 27, those having the highest concentration. So we finished our column, and we ran GOT quick assays on all of these. And what we found out was that 25, 26, and 27 are the best test tubes that say the highest concentration. All right, so we've done all 30 of these. We figured out 25, 26, and 27 really tend to be the best. So we're going to take those 3 and we're going to concentrate them and do our gel next. I want to show you something else. What we also did was determine the protein concentration. And this is using the Folin assay, and sometimes known as the Folin-Ziauketu assay. And what you do is you create a standard curve. And so you can see that there's 6 test tubes here, and they progressively show darker concentration, and we show increasing concentration. We use BSA, bovine serum albumin, as just a generic protein to show this. But then we also assay fraction 1 and fraction 2 to get their concentrations. And we actually did this for the other compounds as well. But noticing that our fractions have higher protein concentration. It doesn't have not as much as the total, but it has a good concentration. We're going to give you these values for FR1, FR2, and a couple of the others in our final data table. But getting total protein concentration is also a good step to get to confirm that you have protein present and to see how much is there. In addition to this, we're going to take our proteins from 26 and 27, and we're going to run an SDS page gel to confirm the presence of GOT. All right, so we're back for our final analysis. So we've looked at GOT activity along the way. One of the final things that you typically always do in a protein isolation is run an SDS page gel. All right, so we know we have a specific activity for GOT, and we ran the GOT specific activity. But a protein gel is always helpful to make sure you have the correct molecular weight. Another physical aspect of this. All right, so one of the things that you can notice is that we have several lanes on here. This first one is our molecular weight marker, so notice there's a whole bunch of those. One of the keys that we want to make sure we notice is that this marker right here is about 48,000 Daltons, the one that's right there. That's going to be key because our GOT is a homodimer, means 2 polypeptides that are 45,000 Daltons big. And so notice there's a nice line all the way across here indicating that we have GOT present. Now let me show you what each column represents. So we know the first one's a molecular weight, 45,000. We should hone in on that. This next one, notice lots of bands, lots of intense ones, even at 45,000 Daltons. And this is our FR1. Notice here's FR2. And so notice we have a little bit of intensity of some things, and so higher protein concentration. And then we go to AS2, and we've gotten rid. AS2, our goal was to get rid of some proteins, and we see fewer bands, sort of higher and lower. They're still there, but it doesn't mean they're zero, but they're just fewer AS2. And AS2D, just the dialysis. So notice again, it's this AS2 and AS2D are somewhat similar. And then our final step was after the CM column, and so this is tubes 26 and 27, and I ran tubes 2 different concentrations. But the thing you'll notice is that the brightest band really is this one at 45, and the other bands are lighter. There is this one which is, means there's some sort of contaminant sticking around. But nonetheless, as you go from this side to the next, you notice that this band at 45,000 Daltons sort of grows in and gets darker, meaning that it is higher concentrated after the CM column, which is what we want, than any other proteins. That means along the way, the heat denaturation, the ammonium sulfate denaturation, after the column, we actually kept getting more of our GOT, which is the goal of this experiment. All right, so this helps us to bring to a close the experimental part of this experiment 7. One of the things that we'd like to finish with is a purification table. All right, so a list where we put all the fractionation steps and all the volumes and activities there, and also think about the purification. All right, so let's fill this in. So again, we had our fraction 1, and this is our crude homogenate, and remember we said that this was 75 milliliters. When we did our Folin assay, we figured out that this had a concentration of 11.9. Its activity was 1140. This was the total GOT activity. We got by taking activity we found earlier and ultimately multiplying it by the volume here. And then we had specific activity. And again, this is really thinking about that, so 95.8. We talked about yield. This is the percent yield. Of course, we're starting off with FR1. That's 100% yield. That has all of our GOT from that particular sample. We're going to put it on there. So that gives us a full purification, which we do because that's really our starting point. So we just say it has a full purification of 1. Our fraction 2 was 35.2 milliliters. Again, because we got rid of a lot of proteins by heat denaturation, notice the concentration went down to 6. We also got rid of a little bit of our GOT, so our activity went down. The specific activity. Here again, the specific activity should always go up if things are working well. Percent yield, we actually went down, again, because we lost some GOT along the way. We know that that's going to happen because we're performing steps that get rid of proteins, and we inadvertently get rid of some GOT. All right, so AS2, we started off, this was 3.6. This was pre-dialysis. All right, so this is after we added the ammonium sulfate to the bulk, got that bulk, and we ended up with 3.6 because we pelleted all of the GOT or as much as we could and then redissolved it in about 3 milliliters of our buffer. However, the solids take up a little space, so it's 3.6. The protein, again, we lost a good bit of protein, and this, as we expected, really we would. We have activity still. Again, the total activity is going down. However, as we know that the specific activity, specific to GOT, is actually continuing to go up. But again, we're losing some GOT along the way. Actually, wrote this in the wrong place. All right, so this one is 1 point. Let's just erase that and make that look clean. After we dialyze, again, we lost a little bit of volume just from dialysis. That ends up here. And again, our protein, as we expect, goes down. It's a really good sign when, again, your specific activity continues to go up. And so we're continuing to see that. All right, and finally, our pooled CMC. All right, so these are our 2 fractions, 26 and 27, that we had there again, pulling those together. And again, we see a protein concentration here. All right, so filling all this in, one of the things that we can notice is, again, the protein volume, of course, continued to go down because we fractionated that. The So again, the protein concentration, it also went down. Again, we at smaller volumes, so we also lost a lot of protein. Our total activity went down. However, the exciting thing is that our specific activity continued to go up. Again, that's about 1,500. And again, that shows it's specific to the GOT, really based on the volume that we see for that and then the concentration. The yield went down, but our full purification went up. So we basically purified the protein and made it 15 times more pure than we started with. All right, so not a bad purification. Again, oftentimes you might see this full purification, and this can get into the thousands if you really ramp this up and do a couple of steps of chromatography and maybe solve for some bulk. So this isn't the best in the world, but it's actually still a good result that we ended up. And we saw that with our SDS page, that we ended up with mostly GOT and a few other things. All right, so in this particular experiment, we've been able to finish off our purification of GOT. All right, so we finished up with dialysis. We were able to take the dialysis. Then we did some CM gel chromatography, and that was a big part of what we did. And then we analyzed the overall part of this by SDS page, and we brought all those together to make a purification table. Right, and that purification table is just a nice, tidy way to bring together all of our results that we've done in Experiment 6 and Experiment 7. So as we finish up in your report, I want you to answer a couple of things. So why was cation exchange chromatography used instead of anion exchange? What was the purpose of the SDS page analysis? And what were three main steps? And this is overall in Experiment 6 and 7. We're used to separate glutamate oxaloacetate transaminase from pig cards.